Okay, I'd like to show you an example of figuring out the pH for a weak acid solution. So let's look at this problem here. It says the Ka of hydrofluoric acid is 6.8 times 10 to the minus 4. What's the pH of a 0.35 molar aqueous solution of HF? All right, so this is a weak acid. Now you might ask yourself, how do I even know that? Well, there's maybe two ways. One way is I gave you a list of 6 acids. If you're not one of those 6 strong acids, every other acid in the world, and there's lots of them, they're all weak acids. The other way you would know is that you see a K value, Ka, equilibrium constant. If you see an equilibrium constant, that's another big tip-off that we are looking at or dealing with a weak acid. All right, so weak acids, to figure out their pH, we have to use equilibrium. So we're going to start ourselves by just getting ourselves going by, first off, if there's an equilibrium problem, weak acids will be equilibrium problems, you're going to want to start by writing out the reaction. HF plus H2O. Now, acids, there's no other option. They gotta make hydronium. That's their whole goal in life. So we're gonna write hydronium. And that's coming from the hydrogen going over to the water. The other product is whatever's left after that acid loses its hydrogen. In this case, that would be F minus. All right, so this is equilibrium. So just to kind of be clear about that, we'll write our arrows going in both ways. All right, so you got your reaction. Now, what else is going to help you? If it's equilibrium, 2 other things. This is going to help you organize your numbers and do your calculations. And those 2 things are set up an ice table and then set up what K equals, the equilibrium constant. The equilibrium constant, that's always products over reactions. All right, so the K just reminds me that we're talking about an acid reacting with water. All right, so it'll be the concentration of hydronium times the concentration of F minus divided by the concentration of HF. Now at this point, we should be in pretty good shape. So I do all that prep, and now we're going to look at the numbers, all right? And now we're going to look at, we got everything set up. That's a good habit to be in, okay? Now, if you're wondering, I ignored water. That's because water's a liquid, so we're not even going to put it in our equilibrium expression, K. Water's not in there. We're not going to do any math for water because it's a liquid. The other things are aqueous. All right, AQ. Okay. Now, as far as the numbers go, I got 2. They're giving me the equilibrium constant. We'll get to that one in a minute. We're definitely going to need it. And then they also tell me that we've made up a 0.35 molar solution of HF. So the initial amount is HF, is 0.35. We're not, in this case, putting in any hydronium or fluoride. If I don't say anything about it, you didn't put any in, it starts off at 0. So we don't know any equilibrium amounts. So this is definitely where we're going to have to do like solving for X. All right. So you don't know any equilibrium amounts. It's got to be a solve for X kind of problem. So to get to X, we're going to think about how things, or what X means. We're going to think about how things change. The things on the right-hand side, they're starting off at 0. They got to go up. X. Notice the coefficients are all 1. That makes life a little easier. The fluoride, same coefficient 1. It's going to go up too. So when nature does this reaction, she's going to generate a little bit of product. We're going to calculate how much, and that is going to be X. Now, at this point, that means we have to use up some of our reactant. It's going to go down by X. So if we put it together, I and C, put those 2 together, it gives you the equilibrium amount. HF starts at 0.35, it goes down by X. Hydronium goes from 0, add up X, it's X, and so is fluoride. All right, so we're going to really solve for the amount of H3O because we know once we get the amount of H3O, if we take the negative log of that, that'll be our final answer. That'll be our pH. So X is basically that hydronium amount. All right, so let's go ahead and plug in and solve, okay? So you got to have the constant. In this case, I gave it to you, and most of your homework, you'll just see it in the problem. You might look it up in the chart I gave you in class too if you had to, but most likely you'll just see it in the question. So it'll be 6.8 times 10 to the minus 4 equals x times 0.35 minus x. All right, now at this point, we're going to do a math little simplification that's going to be really common for, it turns out, acids and bases. And this is all because, and maybe I should switch to another color just for a minute, that if you look at equilibrium constant for an acid, they're always pretty darn small. And they're really small, usually compared to the solution we've prepared. So because those numbers are so pretty drastically different, it allows us to simplify this thing by getting rid of an x, not all of them, just the x's after any plus sign or minus sign. So for right now, there's just a minus sign. So we're going to get rid of that x on the bottom that follows the negative sign. So this simplification used all the time in chemistry class, in this class at least. And the way you know you can do it, again, is if you look at those two numbers that I've got arrows going to, the equilibrium constant and the concentration of the acid. If they're 10 to the 3 apart, 1,000 apart, this simplification will work. If they're closer than that, you would have to keep going with that x on the bottom, and you'll end up doing the quadratic, which if you can avoid it, hey, I'm all for avoiding it personally. All right, so let's just double check. They're 10 to the 3 apart. 10 to the minus 4, the number on the bottom would be like 10 to the minus 1, if you move the decimal over. So they're 3 apart. That's perfect. That's totally great. We're kind of right on the borderline, but pretty much 10 to the 3 apart, right? Yeah, 10 to the 3 apart. Excuse me. All right, so let me erase what I just wrote there. And with that simplification gonna work for me, let's keep going with the math. All right, so we're gonna get, I gotta switch back to the pen. There we go. 6.8 times 10 to the minus 4 equals x, and then I can write x times x, but let's go ahead and make it x squared times 0.35 on the bottom. And from here, we'll do a little more math. We got to solve for x. Okay, so I guess next thing, cross multiply. So when you cross multiply, you should be getting 2.38 times 10 to the minus 4. That would equal x squared. A little more math. You got to get x, not x squared. So what do we do? Square root. That should do it. All right, and if you do that, if you and your calculator are getting along, it should be 1.54 times 10 to the minus 2. All right. So the math isn't too bad if you realize that, hey, you can simplify. Most of the time you can. There might be a chance or two that those two numbers that I pointed out earlier are too close together, and then you get the math is a little more complicated. All right. So that number we just came up with, that is the amount of hydronium. That's what X is. It's the amount of hydronium. That's the one we care about. It's also the amount of fluoride, but who cares about the fluoride? We care about the amount of hydronium. So at this point, we'll just take it and do the log of it, the negative log of it. And if you work it out, when you take the negative log of that number, you get 1.81. All right. So it's always a little hard to know for sure that you've done the math right. One way you can know is, I suppose, we put an acid in water. You better get an answer less than 7. Acids have pHs of, between 1 and about 7. 1.81. That sounds pretty reasonable to me. Okay, so hopefully this example will help you a little bit if you're a little worried about this topic. The good habits, that's what I keep telling you, because I really think they're going to help you. Write out the reaction, get a way to organize what's going to happen, and then start thinking about the numbers and where they fit. So organize with your ICE table, set up what K equals, and then hopefully it'll just be a little math and not too hard math. All right.